Let's see, breakout.
I'm sorry, what's going on now?
Oh, I think we're just trying out the question. So the first part is to simply compute the optimum of this optimization problem. So you want to minimize x squared. So x is simply a real number, subject to the constraints that x is greater than or equal to epsilon. So this is a convex optimization problem. Its optimal value is p star. You're supposed to find out what p star is.
Okay, got it.
So I'm going to close the breakout rooms now. So what's the answer to this question? What is the optimal value of T star?
It's 0 if epsilon is less than 0 and this epsilon is epsilon is greater or equal to 0.
Yeah, so it's 0 if epsilon is less than or equal to 0. Otherwise, it's?
Shouldn't it be epsilon squared?
Yeah, epsilon square, sorry.
Okay, yeah, it's epsilon squared when epsilon is greater than or equal to 0, is greater than 0, right? Why is this the right answer?
Since it's a parabola. Since we're just looking at a parabola.
Oh, yeah. So I guess like maybe one way to do it is that, like, x squared is a positive function over the real numbers. So x squared is always greater than or equal to 0. Right? So when epsilon is less than or equal to 0, you can set x to 0 and you achieve this lower bound. Right? So when epsilon is less than 0, the optimal value of this objective function actually occurs within your constraint set. Right? And in this, and now let's consider the alternate case when epsilon is greater than 0. Now in this range, from epsilon to infinity, x squared is an increasing function, right?
Yes.
Because the derivative of x squared is 2 times x, which is always greater than 0 and epsilon is greater than 0. Right? So the lowest value this function can take is at epsilon.
So it's just a matter of whether or not the constraint is active, right?
Yeah, it's a matter of the constraint is active.
Okay.
Yeah.
Could you explain your reasoning for why when epsilon is less than 0? I mean, it makes sense like when you think about it geometrically, but you're explaining a different way of like active constraints.
So when you think about like active constraints and inactive constraints, one thing you could do is let's suppose that this constraint did not exist. You don't have the constraint that x is greater than epsilon, and you're just trying to minimize this function. Like, what is the lowest value that x squared could possibly take?
0.
Yeah, so the lowest value it could possibly take is 0, right? And it attains that value at x is equal to 0.
Yeah.
Now, if you know that x is equal to 0 lies in this constraint set, then you don't need to do any more, right?
Oh, that makes sense. Yeah, thank you.
Yeah. So
Thank you.
that's why when epsilon is less than 0, you can just set x to 0 and you obtain 0. Otherwise, it's epsilon squared because this function is increasing in the constraint set.
Thanks.
Yeah. So that's kind of the idea. But this made sense, right? Okay. So part B simply, I guess, asks you to compute the Lagrangian of this function. So what is the Lagrangian?
Just x squared plus lambda multiply epsilon minus x.
X squared plus lambda times epsilon minus x, right? Right, exactly. So this is the Lagrangian. So you get epsilon minus x here because you need to convert this to a less than or equal to constraint. So what you do is you switch the x to the other side, and you rewrite this constraint as epsilon minus x is less than or equal to 0. And now it's in the standard form of an optimization problem, so you can write the Lagrangian in this way. Did this make sense?
Yeah.
Okay. So part C asks you to compute the dual function. So you want to compute g of lambda. So this is a function of lambda, which is the minimization of the Lagrangian with respect to x. And this is a quadratic function. So it's a quadratic function whose leading coefficient is 1. So this is like a convex quadratic function if you just look at it as a function of x. So you can find its minimum by taking its derivative and setting it to 0. Okay, so let's do that, and then for the next 2 or 3 minutes, and then we can get back to this. So what is the derivative of this function in terms of x?
2x minus lambda.
2x minus lambda. So if I set this to 0, the optimal value of x should be lambda over 2, right?
Yeah.
So now if I plug this into this expression here, I get that g of lambda is equal to lambda squared over 4 minus lambda squared over 2 plus lambda times epsilon, which is equal to minus lambda squared over 4 plus lambda times epsilon. Right? So now your dual problem is simply maximize g of lambda subject to lambda being greater than or equal to 0. Right?
Mhm.
Hey, could I ask you to explain the intuition of why we're doing the min and then the max of the dual function? I know it follows from the min-max theorem, but if you could just give like a 1 or 2 sentence summary, that would be helpful.
Yeah, so I think there are like many different perspectives of the dual. So like there's like the symbolic intuition that you get from like just doing the math. So once you do this min-max flip, you get a bunch of lower bounds on your final problem. And hopefully those lower bounds in some cases are actually attain the value p star that you're looking for. That's, I guess, like the most symbolic way to look at it. The way I tend to look at duality is like, you're trying to prove that this value p star is going to be the optimum. right?
Sure.
So I guess with duality, what you really want to show is that like maybe if I have some guess value P star for the primal optimal, I want to show that P star is in fact the primal optimal, right?
Okay.
And I can do that if I can exhibit a bunch of lambdas, right? If I can find a bunch of lambdas such that this combination also attains its optimal value at that particular point P star.
Okay.
So in some sense, it kind of converts like maybe you having like several different constraints to an optimization problem to like an unconstrained optimization problem.
Okay.
So somehow it's saying that like you have this really broad class of optimization problems that are all captured by this optimization problem over here.
Okay.
And like one of them has like the exact same value.
Okay. Thank you.
Yeah, I mean that's so in some sense it gives you like a proof that this is in fact like the optimal value. But I don't think like maybe that was entirely clear. But hopefully you'll see more of that once you learn about like the KKT conditions and so on in the next discussion.
Cool.
I mean, the way we show this strong duality hold is by showing D star equal to P star, right?
Yeah. So in part D, you simply have to compute D star, which is the dual optimal, and show that D star is equal to P star.
Okay. But doesn't the minimized value of D star depends on the value of epsilon?
It does. It does.
Yeah. So okay.
That gives you kind of a clue, right? You know that P star depended on epsilon. So when epsilon is less than 0, P star was 0, and when epsilon is greater than 0, it was epsilon squared. So that means that somehow the value of D star should also depend on epsilon, right?
Yeah.
Or like, if D star was actually equal to P star, you'd want to show something like this. You want to show that D star is equal to 0 when epsilon is less than 0. Otherwise, it's equal to epsilon squared when epsilon is greater than equal to 0. Right? So if you want to show this, it has to depend on epsilon in some sense.
Yeah, I just took derivative and found that lambda equal to 0, so it doesn't depend on epsilon.
So you took the derivative with respect to lambda.
Yeah.
So that would be.
Oh yeah, it did. Sorry, I just miscalculated.
Oh no, that's okay. So no, that's okay. So why is D star equal to 0 and epsilon is less than 0? So so this gives you a clue, right? You probably should be breaking it into cases. So let's consider case 1, where epsilon is less than 0. So case 1, epsilon is less than 0. And your problem now is maximize for lambda greater than or equal to 0, negative lambda square over 2, plus lambda times epsilon. Right? What is the largest value that this thing can take? And you should try and use this fact that epsilon is less than 0.
I'm sorry. I think the due function is minus lambda square divided over 4.
Oh wait, yeah, it's over 4. Sorry.
It's over 4, right?
Yeah, it's over 4. Sorry.
Thank you.
Yeah. Okay, so let me just give like a short clue. This is always a negative number, right? Because it's minus lambda squared.
Okay.
And since epsilon is less than 0, this is always a negative number, right?
Yeah.
So what can you say about the sum of these two?
Oh, it's
Less than 0.
Yeah, so the sum of two negative numbers is always less than or equal to 0. Right? For all positive lambda. Right? Does this make sense?
Yeah.
Yeah.
Okay. Can I achieve 0?
Lambda can be equal to 0, right?
Yeah. So I could set lambda to be equal to 0.
Uh-huh.
And I know for all positive lambda, this is less than or equal to 0.
Okay.
Right? So the
Yeah.
optimal value of d star in this case is 0. Because I have this lower bound for everything here. And I can actually achieve 0. Does this make sense?
Yeah.
So that's case 1. What about case 2? So epsilon is greater than or equal to 0. So let me just poll again. Did this make sense?
Yeah,
Yeah.
this step makes sense.
Okay.
I just have a question about the left side of the board. Like when epsilon is less than 0, so why d star is equal to 0?
Oh no, this is what we want to show. Sorry.
Oh, okay. Okay, so we showed this. Okay.
Yeah. So we showed this part now.
Yeah, yeah. Oh, I got it. I just
Okay. So now, again, the question tells you that you need to show that in this case, d star is equal to epsilon squared, right?
Yeah.
How can I go about doing that?
Set derivative equal to 0.
Yeah. So let's try this approach, right? Like let's just assume that this constraint was not there. Okay. And then I'm going to take the derivative of this function.
Why do we have to assume the constraint's not there?
So in general, if you're, let's say you're trying to approach one of these optimization problems and you want to reason about its optimal value, one thing that you could do is ignore the constraint set and just figure out what the unconstrained maximization of this problem is going to be.
Okay.
And let's say I find that it's maximized at some point lambda star. Okay. Now, if lambda star lies in the constraint set, then that has to be the optimal value of the function, right?
Yeah.
So that's kind of the idea. So
Okay.
our first approach is like, okay, we don't quite know. Okay, so we want to figure out what the optimal of this optimization problem is going to be. So our first approach is going to be to ignore the constraint and figure out what the optimal value should be. So, and so we're trying to like maximize this quadratic, but it's a quadratic with a negative leading term. So you can optimize it by setting its derivative to 0. So what is the derivative of this function?
-2 lambda plus lambda or plus epsilon.
Yeah, so it's negative lambda over 2, right?
Oh, whoops.
By 4 here. But yeah, so it's negative lambda over 2 plus epsilon. And now we're going to set it to 0. So you get lambda is equal to 2 epsilon. So does this lie in the constraint set? So remember that the constraint set is that lambda is greater than or equal to 0. And we are in the case that epsilon is greater than or equal to 0.
Yeah, it does lie.
Yeah, it lies in the constraint set. Right? So that means in this case, you can simply plug in 2 epsilon into this formula. What do you get when you plug in lambda is equal to 2 epsilon?
Just epsilon square.
So you get this value, right?
Yeah.
Because for the first term, it's 4 epsilon square over 4, so it's negative epsilon square. The second term evaluates to 2 epsilon square, so when you add them together, you get epsilon square. So you prove B star, so now you've actually shown me. So you proved. So this means that D star is equal to P star, right? So does it make sense?
Sorry. So for the, on the right side of the board, why we didn't take the derivative also?
Oh, we took the derivative.
I mean the case 1.
Oh, case 1. Case 1 is okay. So let's say we took the derivative, right? Now, if you take the derivative, like you still get the same answer. Lambda star is 2 epsilon, but this 2 epsilon would not be in your constraint.
Because lambda is bigger than or equal to 0.
Yeah, because
So
lambda.
that wouldn't be helpful, right? If we just take derivative.
Yeah. In this case, it wouldn't be helpful.
Okay.
So I guess one way to look at this function is like, let's say I plot this function, right? Negative lambda square over 4 plus lambda epsilon. This 0.2 epsilon, let's say it's somewhere here. What this means is that the function looks something like this. Because it's a negative quadratic. And now that you know that the function looks like this, you know it's decreasing when lambda is greater than or equal to 0 in this range. Right? To the right of the y-axis. So the optima will occur at like lambda equal to 0. So that's like maybe a graphical way of seeing it. But essentially this constraint is active as this. That's what's happening. Did this make sense?
Yeah, but usually, like, would you just take derivative first to see if it, like agree with the constraint or not, or when you meet this case?
Yeah, I would say it's a more systematic way of like taking derivatives.
Yeah, to see first if we can solve it, and then if not, we choose some trick to solve it, right?
Yeah, basically.
Okay.
Yeah, that's what I was gonna ask. How did you know, like at the beginning, that we need to split it up into 2 cases?
So in this case, like I think, okay, if I had to do this myself, and somebody did not tell me that P star equal to D star, so I didn't know the strong duality held, I would actually do this. So I would compute the derivative, I'd see where this point is. In the first case, you would realize that it's not in the constraint set, but then you like plot out the function and you see that the optimal occurs somewhere here.
Okay.
In this case, like I split it into two cases because the question already tells you in some sense that strong duality rules. So you know that this is what you want to prove. So this gives you a clue as to how you should split it up.
Okay.
But if you didn't know the strong duality held, you should probably do something else. Did that make sense?
Yep.
Yeah.
Awesome. So the next question, I guess, is simply taking like the dual of a linear program. So let's move on to that. Let me pull it up. So is this question clear?
Yeah.
Okay, so in this question, like the constraints are equality constraints. So the dual variables that you introduce here can be unbounded. They're not constrained by being greater than or equal to 0. Okay, what do you have to do? The first part is you want to compute the Lagrangian of this function with respect to x and 0. So what is this going to be?
Oh, just C transpose X plus mu times AX minus B.
Plus,
Lambda. Oh, mu. Okay. Whatever.
yeah, it's a mu transpose AX minus B. Right?
Yeah.
And to see why this is true, I guess like maybe break down A into its rows. So let's say the rows of A are A1 to AM. The Lagrangian of this is simply going to be C transpose X plus summation mu I. So each of these constraints will have like its own dual variable. So AI transpose X minus BI. But this is simply the same as C transpose X. And let's say you vectorize the mu. So now you look at mu as a vector. And then you can write this as A. Does this make sense?
Yeah.
So for the next part, you want to minimize the Lagrangian with a fixed mu with respect to X. So you want to minimize this function here. So minimize with respect to X. So how do I approach this problem?
Take the derivative with respect to X.
Yeah, I can take the derivative with respect to X. Okay. What am I going to get?
C transpose plus U transpose A.
Plus, so I guess that would be A transpose mu, right? No, it is. I guess like this is going to be mu transpose A x, right? And this is simply A transpose mu transpose x, right? So,
Uh-huh.
so this is the gradient of the function with respect to x. Okay.
Is U transpose A the same thing as A transpose U? It is, right?
So U transpose A is like it's like a vector. So A transpose U is a column vector.
Okay.
But yeah, they have the same entry. They just transpose of each other.
I guess it's a question is after you take the derivative, like A transpose U, just transpose X becomes just A transpose U, right?
Yeah.
Yeah.
So this is the derivative of the function. But so when is the derivative equal to 0? It doesn't even depend on x, right?
Right.
So this derivative is only equal to 0 if t plus A transpose mu is equal to 0. Right?
Yeah.
So that means that unless this happens, the value of this minimization problem is negative infinity. Does that make sense?
Yeah.
Okay.
But then like that's not helpful.
What? Oh, this is helpful in defining your dual program. So this tells you that let's see, it tells you that the minimization over x of your Lagrangian, it's negative infinity if this is not true, right? If C transpose plus A transpose mu is not equal to 0. Otherwise, it's just negative mu transpose B. Right? So this tells you something, right? Wait, so does it make sense?
So can you explain again why otherwise it would be equal to negative mu transpose times B?
Oh, this thing here?
Yeah.
Oh, okay, sure. So what I'm going to do is I'm going to break this into the term that depends on x and the term that just depends on mu and b.
Mm-hmm.
Okay. So I'm going to write this as C plus A transpose mu transpose x minus mu transpose b. Okay. So this is the same as this.
Yes.
When this is equal to 0,
Oh.
this will be equal
Okay.
to so that's why you have this character. So does this make sense?
Yeah.
Yes.
Okay. Okay, awesome. So now we know what our dual function is going to be. But this suggests something. So this says that like we should probably have this being equal to 0 as a constraint in our dual problem. the maximization of negative mu transpose B subject to the constraint that this is equal to 0. So C plus A transpose mu is equal to 0. Right? Because when it's not equal to 0, this objective function goes to negative. Yeah, and yeah, this is just like a dual optimization. So does this make sense?
Yeah, but then how do we solve that? Isn't that another problem that you need to use like Lagrangian for, because it's a constrained optimization?
Oh yeah, yeah. So it's yeah, you can't solve this either. So
So what's the point?
but yeah, you can't solve this either. But I think this question was just meant to like give you examples. But it helps you design algorithms. So
Okay.
for example, like so, let's say you had an algorithm that always maintained a pair. So it maintained an x and it maintained a mu, right? And like I always knew that x was feasible for the primal and mu was feasible for the dual. Okay. So x satisfied this and mu satisfied this. So if I'm in a situation where value of C transpose X was equal to the value of minus mu transpose B, then I can basically stop my algorithm, right? Because I found a point where the primal optimal, where the primal value is equal to the dual value.
You say that again, sorry.
Oh, okay. So let's say I had a pair of like feasible primal and dual points, right? So X satisfies this equation and mu satisfies this equation. So X and mu satisfy both of these constraints, right? So I know that P star is less than or equal to C transpose X, right? Because X is just one feasible point and P star is like the feasible point with the minimum value.
P star is the one from C, right?
So yeah, so P star is the optimal value of this problem. And D star is the optimal value of the dual problem. So if I solve this problem, the value would be P star.
Got it.
Is that clear?
Yes.
So, and since mu is a feasible point for the dual, you know that minus mu transpose B is less than equal to the dual optimum, right? Because the dual is a maximization problem over mu.
Makes sense.
So, and then if I told you that, and let's say that you were able to plug in these values for mu and x, and you were able to see that they were close, then you could automatically stop, right? Because you know that D star is less than P star. So does this make sense? So you know that D star is lesser than equal to P star, lesser than equal to C transpose X. The thing is, you don't know what D star and P star are, right?
Yeah. Yeah.
But you have some mu and you have some X, such that these two values are close.
Oh, so you want to shrink the distance between the values so that the distance between D star and P star also shrinks, right?
Yeah, yeah. So if the distance between these two are small, then the distance between D star and P star are also small.
Oh,
So how do you go about like solving that?
Yeah, so yeah, I think you'll see some classes of algorithms like through the course of the class. So maybe like there are some simple gradients of gradient descent, which also something. Yeah, but like there are gradients of gradient descent which can actually solve the problem. And I think you might see more of them as a class for later.
Okay, so for now, we don't need to know.
Oh yeah, for now you don't need to know. You don't need to know.
Okay, cool. Thank
Yeah, so this question was basically about like being able to like compute the dual. It's like a practice question in computing dual. Okay, so I guess like maybe that's the end of the discussion. Yeah, so a little bit about this time.
Going to be Zoom as well.
What?
Is lecture tomorrow going to be on Zoom as well?
Yeah, I think it's going to be on Zoom.
Okay, cool. Thank you.
Do we still have webcasts of the, I mean, Zoom version lecture?
Yeah, I think we'll definitely upload like a webcast.
Okay.
Yeah. Yeah. Maybe the discussion is a little bit rough today. Like maybe for next time we'll use like an iPad or something.
I mean, is discussion also recorded also like in the future?
Yeah. I think we're going to be recording this.
Okay.
Okay. Cool. So I think maybe that's it for this discussion. Like, if you have any feedback, please let us know. Like, yeah.
Thank you.
All right, thanks.
Thank you.
Thanks.
you.
Yeah.
Thank you.